We know that as we grow, the hurdles will be more. Each time we are washed away, we bounce back to the shore. We know we lead the way, keeping odds at bay. To see the sunrise tomorrow, inspire the world to follow. हम सीधे जहाँ GIS है हम है गुरुकुल हमारा.
Okay, so in the module number 2, in the course curriculum of EES3 MC1, that is electrical machine 1, we are discussing DC generator. And in our last two classes we have discussed about constructional feature and EMF equation, and then we have discussed armature reaction of DC machine, and today we are going to discuss types of DC generator. Okay, and this is the objective or outcome, to become familiar with the classifications of DC machine. So let's start lecture number 3 on classifications of DC machine. So my motto is to discuss on classifications. Now, whenever we classified something or anything, basically it is done based on some parameter. Similarly, here in case of DC machine, we can classify DC machine based on method of excitation. So classification basically done based on method of excitation. Now what is excitation? Excitation means to initiate some action, to initiate some action. So what is the initial action in any electrical machine? What is that initial action in case of DC machines? It is to set up magnetic field. It is to set up magnetic field. That means the term excitation in electrical machine means providing a current to the field winding in order to produce magnetic field. So we provide current in the field winding and that will produce magnetic field. Now we have seen in case of DC machine, it's required stationary magnetic field for its operation. That means the field system is the stationary part of the machine, or rather we can say field system is in the stationary part of the machine, which is called stator. So therefore if a DC current is passed through the stationary field winding, wound around that main poles, a stationary magnetic field can be produced. Now depending upon the source from which this mentioned DC current called excitation current or field current is drawn, the machine are classified into two broad categories. So depending on source of excitation current, depending on source of excitation current, DC machines are classified into two categories. One is called separately excited DC machines, and the another one is called self excited DC machine. Okay, now as the name suggests, if the excitation current is drawn from a separate source, then it is called separately excited DC machine. And if the exciting current drawn from same source, if it is drawn from same source, it is called self excited DC machine. Okay, so let's first discuss the separately excited DC machine. So first we are going to discuss separately excited DC machine. Okay, so as the name suggests, I have mentioned the field winding is supplied from a separate DC source, and this DC source with fixed or variable voltage level. So it's drawn from separate DC source with fixed or variable voltage level. And what is that separate source? It can be either a battery, or an AC to DC rectifier, or it can be a DC, another DC generator. It is not only enough to obtain the DC current, but our motto is to control the field current. That means the field current also must be controllable, so that magnitude and direction of magnetic field produced can be controlled as per requirement. So we require controllable field current, so that we can control the magnitude and direction of magnetic field which is producing. Okay, now what is our Ohm's law and what is its purpose? Ohm's law relates the current in a circuit with voltage applied across the circuit and the resistance of the circuit, that is V equals to IR. So I equals to V by R. Now we will apply this Ohm's law to the field circuit in the separately excited DC machine. That means we can write it down, field current IF equals to, suppose we can write it VF or EF, whatever we want, divided by RF. Okay. Therefore, a variable field current IF for a separately excited DC machine can be obtained in different method. So we can obtain this current in different methods. What is that? First one, VF or EF is fixed. RF is variable. So the current obtained from the fixed voltage source and variation of current is achieved by changing the resistance of the field circuit. Okay. So what will be the circuit of this category? Let me draw the circuit. Let me draw the circuit. So there is a source. You can connect a ammeter to measure the current. This is the field system. This is variable resistance, because here voltage is fixed and RF is variable, and I will connect this with variable resistance. This is my RF, this is my RSH, and this is my VF or EF or V, whatever you can write it down, and the current is flowing is IF through it, and the two terminal we can write down Z. Okay. Similarly, there is a armature part. Which one is the rotating part? Okay. So the two terminal is A and A. So this is VF or EF or V or E, whatever you can write, is fixed, and RF variable. Okay. Now what is the second option? The second option is this voltage is variable and this is fixed. So in that case, this is the diagram. So this is now a fixed resistance. Okay. So no need to represent it separately. So what I will do, it will connect it directly. So I can connect it directly. Okay. So in this case, the voltage is variable but RF is fixed. Okay. Now what is the other option? Both are variable. Both are variable. Okay. So what will be that circuit? So that circuit is, there is a voltage source So both are variable. So what I will do, I will connect a resistance here, and then I can vary this resistance, which is again connected with the supply, so we can vary the voltage also. So a ammeter is connected, and then the field. Okay, field system is connected. So this is RSH, this is Z, ZZ, this is V. Okay, this is plus minus, the current is IF, and here there is a armature A, AA. Okay, and this voltage is voltage across the field VF. Okay, so here the variable voltage is obtained by using a potentiometer. So we have used the concept of potentiometer. Okay, so we can draw the same figure again in different way. How is that possible? So I will not here use that potentiometer. Okay, so what I will do, I will directly connect this, and I will use a variable source itself. Okay, this is my IF, this drop is VF, this is my shunt field, and I will here a variable resistance here. This is Z and ZZ. This is my RF. Okay, so two way we can obtain this variable voltage and variable resistance. So this is for separately excited DC generator. Okay, now what should be this separate excitation equation both for DC generator and DC motor? Okay, so let me cover that thing. So so first, for separate excitation for DC generator. Okay, so generator means mechanical energy converted into electrical energy. So there is a source, potentiometer, ammeter, field. Okay, now this is a generator, armature. Okay, so increase, So here I will connect a voltmeter which will measure the voltage. Okay, armature voltage, that is EA, suppose. Okay, and generator, so output is current is emerging from armature IA, because this is a generator. So now here I will use a double pole single throw switch. This is a double pole single throw switch. A fuse is there. This is the fuse. This is the fuse, and again a meter, and it is connected to variable load RL, and this give my load current. Okay, so let's assume this as U, this is Z, ZZ, and this is IF. Let assume this voltage as UA. Okay, and this voltage UL. So this is the separately excited DC generator. Okay, this is the connection diagram. So you see here in this connection diagram there are two different electrical circuit. One circuit connects the armature of the generator to the load, and the field circuit is separate from the armature and is supplied by external source, this one. So two different electrical circuit is therefore, and therefore the field current IF is separately excited DC generator is independent of its armature current. So IF is not dependent on IA and the armature voltage, which implies that any change in armature current or armature voltage does not change the main field flux phi m set up by the field current. So this IF is responsible for the setting up of field current. Okay, so if there is any change in this current IA, it has no effect on this IF, or rather main field phi m. Okay, so what should be the equation? IA, this current is also flowing, this is also the load current, we can write it down IL. So IA equals to IL, and this UA UL parallelly current, parallel voltage, so these are same, UA equals to UL, and this is equals to E minus IA RA, E minus IA RA. Okay, E is the induced voltage, I is the armature current, and RA is the resistance of this armature. Now what will happen for motor now? So in motor, the electrical energy is converted into mechanical energy. So for motor, for DC motor, connection will be, so we have to provide electrical energy, right? So again, double pole single throw switch, which is connected with a fuse system, ammeter. So I am giving supply to the motor, electrical supply to the motor. Okay. Now giving supply to the motor. So this is Q1. So I will connect a voltmeter here to measure the voltage, DC voltmeter. Okay. So this is the load now, current plus minus. Okay. And this voltage is suppose UA. This is the armature AAA, and this is armature current IA. Same machine now acting as a motor. So from load, current is providing, I am providing current from load to the motor. Okay. So the field system will be the separate one. So this is my field system, which is connected to a variable resistance. Okay. And I will connect a ammeter here, and this is again connected with a fuse arrangement system and double fold single throw switches. Okay. So this is my field current. Now interesting fact is that this is direction is changed. IF, look, IF is getting inside the armature because previously it was emerging from the armature, now it is entering the armature. So this is my also the field current. So this is minus, this is plus. Okay. And suppose this voltage is U2. So now when DC machine works as motor, both the armature circuit and field circuit are energized from external electrical source. Both the circuit, this is also energized from external electrical circuit, this is also energized from external electrical circuit. So both energized from external electrical circuit power source. Now for all normal operation, a single supply source give electrical energy to the entire motor circuit. On some special occasion, like speed control operation, to separate DC source are used. One source supplied energy to the armature circuit and other to the field circuit. So this is the circuit diagram of separately excited DC motor. So what is my network equation? IA equals to IL, same current is flowing, IA equals to IL, and UA, that is armature voltage, UA, that is equals to this voltage U1, and this time it is E plus IAR. So sign got changed. Look, this, it was minus for generator and it is plus for generator machine, because when it is emerging acting as a generator, there is loss in the armature, that is a drop due to this armature resistance, which we have to subtract from the generated voltage or induced EMF. But now the current is getting inside, the polarity got changed, so it is now additive polarity. So now induced EMF added up with this armature voltage drop. So you should always keep that in mind. For generator, armature voltage drop is subtractive. For armature voltage drop subtractive, for generator, and additive for motor. Okay, so this is all about separately excited DC machine, both for generator and motor. One more thing, so what is my this equation for motor? What is my field current? This is equals to Ohm's law, voltage is U2 by resistance. How much resistance? This is shunt field resistance RSH, and this is my external resistance RR. So U2 by RSH plus RR. Okay, so this is separately excited DC machines. Now we will discuss the self-excited machine. Okay, now self-excited machines are basically classified into three main category. Self-excited, okay, so what is that three category? Series, shunt, and compound. Okay, now here it is self excitation. That means the current to the field winding is supplied by the voltage source available across the armature of the same machine. So that we have to keep in mind. That means field winding is supplied by the same voltage source which is supplying armature 2. Okay, now how this field winding connected with the armature circuit depending on, this is the classification. So this classification based on arrangement of field winding with armature. Okay, now this compound motor is again classified into two category. One is short shunt and another one is long shunt, and these two category whether it is short shunt or long shunt again classified into two categories: cumulative compound and the other one is differentially compound. So this is the classifications of self excitation. Okay, so now first we will discuss shunt excited DC machines. Shunt excitation. So in first we discuss DC shunt generator. Okay, so let me draw the figure. So generator So shunt, so that means the field winding connected with the armature, how? In parallel. So there will be a parallel connection. Okay, so there will be a parallel connection. So let me draw in parallel the armature. So this is a again double pole single throw switch with fuse, and this is connected with the load. So this is generator. So here we can represent that armature resistance with a source. So this is the representation of armature. So armature is basically this E, and there is a resistance RA. So this is the electrical representation of armature. Okay, so current will emerge from armature as generator. It will divide it two part. One will go to the field and another one will go to the load, which is IL. And here the armature drop is UA, suppose. So this is my A double A terminal. The field drop is UF. Okay, and this is the complete DC shunt generator circuit. Okay, so what is the network equation? What is the network equation? We can write UF equals to UA equals to UL. Okay, what else we can write? We can write this this RF equals to, sorry, IF, field current IF equals to, what is the voltage across shunt UF, and what is the resistance? It is RF. Okay, so let me assume this one as RR, external resistance. So what is my RF? RF is R shunt plus R. Okay, what is my IL? Voltage is UL, resistance is RL. What is my IA? It is a combination of IF plus IL. What is my load? UL generator. So E minus sign, subtractive polarity, IA RA. And what is my IA? We can put the value this IA plus IL, and the power will be output voltage into output current. Okay, so if we see here this equation, so we can see the field current IF depend on load voltage, because UF is also equals to UL. So we can write it down, UF by RSH plus RR. So instead of UF we can write UL RSH plus RR. So IF is function of load voltage and that regulating resistance RR. Okay, so this is the fact. So if we change the value of RR, we can get our desired result. Okay, so we can say IF is proportional to UL. So therefore we can conclude that field current cannot be fully controllable as it was in case of separately excited generator. So in case of separately excited generator we can fully control the field current, but in case it is depend on the load condition. So according to the load condition the field current will changed. So this is a very important point, that IF is not fully controllable as it was in case of separately excited motor. Okay, so this is all about DC shunt generator. Now let's discuss about DC shunt motor. Now DC shunt motor. So from some external supply we have to provide that electrical energy, because now the electrical energy gets converted into mechanical energy. So from outside we will provide this, and this is my field system. Again double pole single through switch. This is U, this is my load current IL, this is IF, this is RSH, this is RR, and in parallel the armature is connected. Okay, A double A. So the direction of IA will be this. This is basically a resistance, the voltage combination. Okay, so what is the equation? Now equation is the drop across armature is UA. Okay, the drop across field is UF. So you can write U equals to UF equals to U. A. RF equals to again RSH plus RR. Okay, IF is UF divided by RF. Armature current equals to IL minus IF, because IL is now equals to divided two part, IA plus IF, so IA equals to IL minus IF. So now what is my this U? This U is E plus IA RA, or we can write it down E equals to U minus IA RA. Okay, so what is my input power? Input voltage U, current is IL. Now you see here the field current IF depend on U, the supply voltage, and RR, which is the regulating resistance. This RR is basically the regulating resistance. Let me change its a bit little. This is not connected here. Let me connect this. So this is RR is the regulating resistance. So IF is the function of U and RR. So this is similar to DC motor, but what is the difference? That the supply voltage for field current and armature circuit are one for the same. So this is, in case of generator there was a difference, but it is same such as separately excited DC motor. The only difference is the both field and armature getting supply from the same voltage source U. So this is all about DC shunt motor. Okay, now DC series motor. Machine, first generator. So now the series field is connected in series with the armature. So what would be the diagram? I am drawing quickly the diagram. So this is my armature. Now the series field circuit is connected in series with the armature. Okay, so this is my AC series field. This is my armature, and all other will remain same. So it will get supply from the same source with a double pole single throw switch, and armature is connected. This is giving supply to the load RL. Okay, so what is the drop across this armature now? UA. Okay, so I will connect a voltmeter here, and this is my UL, this is my IL, this is my IA, this is AC series field current, or this is, we can write IF also. So we can write down now IA equals to this. What is my UA? Generator subtractive polarity, IA RA. So we can again write down IL IA, because IA equals to IL. Now what is my UL? this is this UL is this voltage minus the drop across this series field, that is IL R AC. And what is my UA? E minus IL RA minus IL R AC. What is output power? P0 equals to UL IL. Okay, so if you see here, IA equals to IF equals to IL. The field current is either equal or proportional to the load current. So any change in the load current causes change in the field current, and field current is responsible for the production of flux. Okay, so when the machine is unsaturated, the flux produced will be directly proportional to load current or armature current. So for series machine, we can write down phi is proportional to IA. Okay, and when it is saturated, phi will become constant. Saturation mean constant. Okay, and this is also hold true for DC series motor also. Okay, so what is the circuit of DC series motor now? So now we have to give supply from external electrical circuit, because electrical energy converted into mechanical energy. So very simple. Series field is there, armature is there. So this is the circuit for motor. Okay, this is U. Okay, sorry, there will be a again double pole single through switch fuse. So now load, it is going inside. So now this is IA and this is IAC. Okay, so we can write down now IAC is also known as IF field current. I am writing instead of IF IAC because this is series. So in shunt machine, in case of IF, we can write down I shunt also, no issues. Okay, so which you can write IA equals to IF or IAC equals to IL. UA equals to U minus IL RAC. So what is my E? UA minus IA RA, that is UA minus IL RA. So ultimately U equals to U minus IL RA plus RAC. And what is my input power? Input voltage U, load input current IL. So this is the network equation for DC series motor. Okay, so in our next class we will discuss about compound excited DC machines. So this is all about today's class. So these are the reference books. Okay, thank you very much.